So now that we know this sort of fundamental principle by which we can generate an expectation of the genotype frequencies in a population given the allele frequencies and vice versa, we can use that to ask the question, is a population in Hardy-Weinberg equilibrium, which is sort of like our null hypothesis. And so let's consider an example here. So this particular case is dealing with a HLA gene. That's the human leukocyte antigen gene, HLA-DQ1. This is part of the MHC complex, which is a very important in the human immune system. And so we're just going to think about a single SNP, a single nucleotide that varies in the population, and we have either an A or a G. And so we can do a very simple study where we can genotype all the individuals in that population and determine what their genotypes are. And we have a total of 17 big A or AA individuals. So this is now a SNP that we're talking about. We have 12 individuals that are homozygous for the G allele, so they're GG. And we have 55 heterozygotes who have the, the AG genotype. And so we have a total of 84 individuals that have been genotyped here. And so we can, of course, calculate the now the frequency of each of those genotypes. And so that's very trivial over here. So this frequency is going to be 17 divided by 84, which is equal to 0.202. This frequency is going to be 55 divided by 84. That is equal to 0.655. And the frequency here is going to be 12 divided by 84. That's equal to 0.143. And whenever you're doing these sort of calculations, you always just want to stick this in the calculator and make sure, of course, that the frequencies add up to 1 so that we know that everything is good. So we have our genotype frequencies here. Now let's go and determine our allele frequencies. So we want to compute the P, which is the frequency of the big A allele, which of course is the frequency of the heterozygotes plus half the frequency of, oops, I said that wrong. This is the frequency of the homozygotes plus half the frequency of the heterozygotes. That's going to be 0.202 from here plus half of 0.655, which is equal to 0.5295. And just to make sure I'm not doing anything weird, we'll compute Q directly from here. So that's this frequency plus half the frequency of the heterozygotes. So that's a mistake here. We want this genotype. And so that's this one, 0.143 from here, plus half the hets, which is 0.655. And that is equal to 0.4705. And if we add P plus Q, it equals 1. And everything is as we expect.